Besides hypothesis tests, we can also conduct confidence intervals, and we can do that regardless of whether we're dealing with one population, two populations, if we're dealing with means or proportions. But for now, we're going to look at when we have one quantitative variable, so that means we're going to be looking at a confidence interval for a population mean. And so here, I've got an example of a whole bunch of confidence intervals for a single population mean. We can see that we're testing, or we're building a confidence interval for mean. We're sampling from a normal population when we're using a z critical value in this case. So here, the true mean is 3, standard deviation is 10, and we're taking samples of size 100. And we know that the larger the sample, the narrower the confidence interval, because the standard error will decrease. We're going to take 50 intervals, and so we've sampled, and so this is our sample of 50 intervals. Now, we're doing this with a confidence level of 95%. And so what we would expect is that 95% of these intervals are going to contain the true mean of 3. Now, that does not mean that we're always going to contain exactly 3. So we're not always going to contain exactly 95% of the time. That does not mean that exactly 95% we're always going to contain that true mean. It means in the long run. So this is where we get this idea of frequentist versus Bayesian statistics. So the frequency idea means that over many confidence intervals, over many samples, we're going to contain that true parameter, right? So this just means the confidence interval captures or contains the true mean 95% of the time. And we can see that. So at this point, 92% of the time, we've contained the true mean. In the long run, out of 1,000 intervals, 95.1% of them contain the true mean. And I even have a nice little website that will illustrate this. So here, I'm going to sample from a normal population. I'm going to take samples of size 5, and I'm going to do a 95% confidence interval. So this is still saying the same thing. 95% of my confidence intervals should contain the true population mean. And the true population mean is represented by this dashed line over here. And that is what is centered on this whole distribution. So I'm going to take a sample of size 5, and we'll see 5 dots come out of this sample, and they're going to form a mean. Sometimes those means might be down to the left, sometimes those means might be down to the right, sometimes those means might be right on top of this line. They're going to vary because we know that our samples are variable. So I'm going to start sampling, and we're going to see if the confidence interval overlaps this dotted line, then we're going to say that that interval contains the true mean. If it does not overlap that line, it's going to be colored in red, and it's going to exclude the true mean. Now, 95% of our intervals should overlap that dotted line. So the first few intervals that we've sampled do in fact contain the line. However, this red interval here does not even come close. It excludes that mean. All of these green intervals, however, overlap our dotted line, and so we'll say that those intervals contain or capture the true population mean. And we can see, based on this bar plot, 43 out of 44 intervals, or about 98%, capture the true mean. And only 1 out of 56, or 2% at runtime, exclude the true mean. Now I can keep going, and we can see that this is going to keep updating, and we're going to stay at about 95% confidence. Now the more and more samples I get, the closer and closer these bars are going to get to 95% and 5%. Now, the question is, let's look at some things. So all of these green dots and all of the red dots, the dots that result in the confidence intervals, those are our sample means. And we can see that they're moving all over the place. That is because we're only taking a sample of size 5. And we know that small samples have large variability, and this variability is represented by the movement of these sample means. The other thing we notice is the width of the intervals. They vary, but they're also quite wide typically. And that width of the interval is also being affected by this small sample size. So now, let's look and see what happens if I increase my sample size. That sample size increase, changing nothing else, should decrease the width of the interval and make my sample means typically closer to the true population mean. So I'm going to go from n equals 5 up to n equals 10. We can already see that my sample means are less variable. They're all tending to be a little bit closer to that true population mean. We also see that the width of the intervals, the length of those bars around the sample means, are narrower. To make it even more clear, I'm going to go to a sample size of 25. My sample means are bouncing around even less now, and the widths of my intervals are even smaller. My variability in my means is decreased because I have decreased my sampling error by increasing my sample size. However, my confidence level, that 95% confidence level, is still the same. 95% of these many intervals that I have built contain that true value. 95% of these intervals are overlapping this true mean. All of them don't, but most of them do. That does not mean that a given interval is going to be accurate. It just means in the long run, I should contain that true mean. Now, let's go back to these notes. To say that we're 95% confident means that if many samples are taken and this method is used to construct confidence intervals, then about 95% of confidence intervals will capture the true parameter. To interpret a 95% confidence interval for an unknown parameter, say we are 95% confident that the interval from whatever our lower bound is to our upper bound contains the true value of our parameter defined in context. Our words matter. Our language matters. We have to say that we're talking about the true value. I need to know the context. But we also have to remember that confidence intervals tell us what values for the parameter are compatible with the current sample. So if we go back to our distribution here, and I'm going to decrease my sample size, we can see that some of these values are different than some of the others. So some of the sample sizes, or excuse me, some of the intervals, some of the values that are compatible with the parameter are quite different for one sample than the values that are compatible with another. This red sample here has values that are parameter values that are compatible with the data that don't include the actual parameter. And that is key. Our data, depending on our sample, will support different values. We see that in this illustration as well. This sample supports values for the parameter that are not the actual parameter. All these other intervals, the green ones, support values for the parameter that are compatible with the parameter, but they are not the same values. This one supports higher values. This interval supports lower values. So we have to think about what this means in a broader context. So let's think. Suppose a random sample of 114 students was chosen and each student was asked how many hours he or she studies each week. The resulting 95% confidence interval for mu was 8.9, 11.8, and of course the units on this is hours. Determine if each of the following is a correct or incorrect interpretation of the confidence interval. I suggest you pause this and then come back and check your work with mine. So for the first one, the interpretation is that 95% of all students in the population study between 8.9 and 11.8 hours per week. This is an incorrect interpretation. This 95% is 95% confidence in our method. It does not tell me about the population itself. This tells me about the long-run proportion of intervals that contain the true parameter. It does not tell me about the number of students that study in that range. The second statement, for 95% of all samples, mu will be between 8.9 and 11.8. This is also incorrect. This is not telling me about the proportion of samples. This is not telling me what mu will be. Mu is constant. Mu does not vary. This is also a misunderstanding about the nature of what the parameter is and what the confidence is doing. The last statement, for 95% of all samples, mu will be included in the 95% confidence interval that results from using this method. This is a correct interpretation. This is, in fact, the definition of what the confidence is doing in this context. So let's think of another situation. Suppose instead the researchers decided they would be satisfied with a 90% confidence interval based on this sample. How would the margin of error change? So that is, how would the width of the confidence interval change if I went from 95% to 90%? Well, in this case, my confidence level has decreased. And so that means my margin of error will also decrease. That means I have a narrower interval. I can see this in my illustration here. So here I'm not going to change anything. I've got my sample size, in this case of size 9. I'm not going to change my distribution, but I am going to go from 95% confidence down to 90% confidence. This is a little finicky. So I was at 95% and I'm going down to 90%. And we can see that this interval is typically narrower, right? So that means I have less coverage. It's harder. I've got less probability of containing that true parameter value. Suppose the researchers repeated the study with a sample of 1,000 students. So back to 95% confidence, but now n equals 1,000 instead of only 114. How would this impact the margin of error? Well, we saw this in my app before. The n has increased, and we know that that means my standard error will decrease. So that means I'm going to have a smaller margin of error. That also is a narrower interval. So I just realized here that this should be about baby birth weight, not average work weeks. So back to our birth weight data. We're going to construct and interpret a 95% confidence interval for the true mean birth weight for these babies. We need a formula, so that's going to be x bar plus or minus t star with n minus 1 times s over the square root of n. Now, what are all these components? This is of the form statistic plus or minus critical value times standard error of that statistic. So my statistic, well, I'm estimating a population mean, so I'm using my sample mean. This critical value, this is a t critical value with n minus 1 degrees of freedom. N minus 1 is going to be 3,170, just like when we had to find the p-value for this problem before. This tells me what distribution to look at. So, to plug in, My sample mean, as we'll remember from before, is 3264.03. My t critical value is 1.9607. And my standard error is s over the square root of n, and that's 602.08 over the square root of 3171. I solve for this, and I get a lower bound of 3243.07 and an upper bound of 3284.99. And birth weight is in grams, so my interval is in grams. Now, where did I get that critical value? Just like by finding a p-value in JUMP, we're going to have to use the distribution calculator to get our critical value. So I'm going to go to Add-ins, to the Teaching Modules, Distribution Calculator. And as before, because I'm using a t critical value, I want to make sure I'm using the t distribution. And I need to enter the correct degrees of freedom. Again, this is n-1, so for our example, this is 3170. Now, the first thing that's going to change is now I have a probability. This is that long-run probability of containing the true parameter value with my intervals, and that is my confidence level. So I'm going to input the probability that I have, 95%, and calculate a value. And the value that I'm calculating is my critical value. So that's the first thing that's different. The next thing I want to do is change my percentile options to a central probability. With p-values, I was doing two-tailed probabilities. With critical value, I have the central probability. So my confidence level is containing, so I'm containing 95%. Then I just enter my my probability, or my confidence level, 0.95, and I hit enter. Now I've got a low and a high, and we can see that they are opposite numbers. So I've got a negative 1.9607 and a positive 1.9607. We can choose either one. I'll use the positive one because it's a little easier to work with positive numbers. And that's where I got my t critical value in my formula, this 1.96071. Alternatively, just as before, I can use the statistics calculator. So I can go to Add-ins, Statistics Calculators, and I can do a confidence interval for one mean. I'm going to use my summary statistics, and I want to do a t interval. And I use a t interval because I don't know my population standard deviation. My sample average is 3264.03. My sample standard deviation is 602.08. And my sample size is 3171. So these are the same values that I had before. I'm using a confidence level of 0.95, and all I have to do now is hit enter. I see my t multiplier. It's the same critical value that I had before. I have the same standard error that I had before. This is s over the square root of n. And I have my lower and upper bounds. I don't know what my true population mean is. That is, I don't know the true mean birth weight of all January 2016 babies born in the U.S. But with 95% confidence, if I were to build this interval over and over and over again using a new sample each time, I'm going to contain that true mean. That does not mean that I have a 95% chance of containing the true mean with this particular interval. So, let's interpret this interval. Using the language we had on the previous page, with 95% confidence, the true mean birth weight of U.S. babies born in January 2016 is captured or contained by the interval 3243.07 to 3284.99 grams. Or we can say the interval 3243.07 3284.99 grams of mean birth weights is compatible with our sample of 3,171 babies born in the U.S. in January 2016 with 95% confidence. If we were interested in whether 3,300 grams, like for our hypothesis test, is a reasonable value, we might compare that to our interval. The distance between 3,300 grams and the upper bound of our interval is small. That is 3,300 minus 3284.99 is only 15 grams. And the width of the interval is wide, 41.9 grams. Although 3,300 grams is not compatible with these data, the effect is small, or the difference is small, and other similar means are compatible. So even though 3,300 grams may not be the true mean, we're probably not concerned if it's exactly 3,300 grams, and something very similar to 3,300 grams may likely be the true mean. So this is why we're coming into this new way of thinking about decision making and considering our data and hypothesis tests and confidence intervals.